All right, welcome to your next lecture in data structure CSE 222. So what we want to talk about today is something called order of complexity. And this is an important topic when we're talking about algorithms in general, things like sorting and searching or trying to find the shortest path through a graph and so on. We'll talk about the order of complexity of an algorithm. And this is an attempt to measure how efficient one algorithm is versus another, but not in terms of just raw speed. Saying how long does it take to sort a bunch of numbers with this algorithm versus that isn't the most meaningful metric. A more useful metric generally is with this particular algorithm, if I have 10 times as much data to sort, how much will that slow down my algorithm? How about this other algorithm? If I add more data to my problem, how does the speed of that algorithm change? And one algorithm we may find when we double the amount of data takes twice as long to sort. That's not too bad. Another one, when we double the amount of data, it might take 4 times as long to sort. Well, that's a big problem if we're going to scale up our data by 1,000,000x. That's going to scale up the time by 1,000,000,000x. So we're interested in the growth in the time complexity of different algorithms. And so this is different from just raw speed. The other thing is speed can be a little deceptive. So for example, I have a program called A, and when I run it, it takes a few seconds to finish. I have another program B, and when I run that, it takes a few seconds to finish. But these are very different programs. And so if I were to run my program and say time A, what it will do is it will execute my program, but then it will give me some statistics. And the statistics I'm getting here are saying it took just over 3 seconds of real time. Real time means wall time, the time that passed on the clock. But user time, that's how much time it took the CPU. And that's showing, rounded off 0 seconds. And then system time is like overhead, so 7 milliseconds, 7/1000th of a second. So this took 3 seconds to complete, but it didn't take a whole lot of CPU time. Now my command B, on the other hand, if I run that, it'll take just over 3 seconds to finish, 3.5 seconds, but it also took 3.5 seconds of CPU time. So almost that entire 3 seconds was spent in the CPU. And it's not a big mystery, right? A is just a simple script that says sleep for 3 seconds, and B is a C program that loops 1,000,000,000 times. So when we talk about how long an algorithm takes, one thing we want to keep in mind is some algorithms, may take longer, but they may be doing a lot of I/O, right? Rather than a lot of sort of CPU-bound calculations. So that's something to keep in mind. But let's look at the growth rate, the complexity of different algorithms. And so let me begin with a simple algorithm. And this is something that you'll work with in the problem set in class. Just kind of a simple single loop. So this is a program that basically reads a number from the user and then loops that many times. And this is typical of, for example, if you had an array of numbers, and let's say there were n numbers in here, and these numbers were not sorted, they weren't organized in any particular way, and you wanted to search to see if the number 17 was in here. Well, really your only way to do this is check the first number, see if that's a 17, check the second number, check the third, and so on. If you find a 17, hey, the number's in there. If you get all the way to the end and you didn't find your 17, it's not in there. So if there are n numbers in this array, it takes n operations. So a simple linear search of an array is an order n procedure. Now if you think about a bubble sort, we take a bunch of numbers and we move through and compare each number to the number after it, and we swap two numbers if the first number is larger. So we would swap these and make a 2 and a 4. We would swap the 4 and the 3. We would leave the 7 because that's bigger than the 4. We would swap the 7 and the 1, and then we would swap the 7 and the 6. And so after one pass through this bubble sort, our number looks like 2, 3, 4, 1, 6, 7. And in that first pass, what we've done is we've put the largest number into this bottom position. So one pass takes n operations and puts one number into the correct position. If I were to do another pass, I would keep the 2 and the 3 and the 4, the 4 and the 1 I would swap, and the 4 and the 6 would stay the same. And now I know that this is also in its correct position. So 2 passes, I get 2 numbers sorted. So if I do a total of n passes, in other words, repeat this n times, I have n numbers sorted. My whole list is sorted. So to do a bubble sort takes n passes, and it takes n operations per pass. That's n squared operations. All right, so let's just look at those two things, something that takes n operations and something that takes n squared operations. So let me put down a value for n, and n ops and n squared ops. All right, and suppose n is 10. Well, this is going to take 10 operations. The n squared algorithm is going to take 100 operations. So we could look at this and we could say, oh, this is worse because it takes 100 instead of 10, but we don't necessarily know that yet. That turns out to be true. But let's look instead at what happens when we go from, say, 10 pieces of data to 20. Since this takes n operations, this will take 20. Since this takes n squared, it will take 400 operations. So we doubled the amount of data, we doubled the amount of time for this first algorithm, but we quadrupled the amount of time for this algorithm. And if we went to 30 pieces of data, now we've tripled the original amount of data. The amount of time for this algorithm also tripled from 10 to 30, but the n squared algorithm went from 100 to 900. It went 9 times larger. And so this is getting worse more severely as our data grows than this algorithm is. This algorithm is linear, right? If we increase our data by this much, the amount of time it's going to take is also going to increase by that much. Whereas this algorithm is quadratic. And so if we increase our data size by a certain amount, the time will increase by something generally larger than that amount. So we have a notation for this. We would say that this linear thing is what we call order n. And this is what we call order n squared. And this is just a nod to the notion, the observation that that this has this sort of n squared behavior, right? It's quadratic in how the time increases. So O(n), we say order n, and that's linear. O of n squared, we say order n squared, and that's quadratic. And there's all kinds of orders that we can have. We could have order n log n. We could have order of log n. We could have order n cubed. We could have order n to the n. We might find order 1, something that takes a fixed amount of time no matter how big the data is. We're going to learn a data structure later in this course called a hash table that theoretically has order 1 performance. So this order of complexity is a useful metric for comparing algorithms and getting an idea how the time required for the algorithm to run changes as the amount of data changes. All right, now a couple of observations to make here. Let's go back to our original table, n and order n squared. And let's look at values of n of, say, 1, 2, 3, and 10. And so our linear algorithm takes times 1, 2, 3, and 10. Our quadratic takes times 1, 4, and 9, and 100. So yeah, 10 times as much data, 100 times as much time. Now, there's a few simplifications we can apply to order of complexity. First, constants don't matter. So suppose we have a linear algorithm, but instead of taking order n, it takes 500 times order n, or what we might be tempted to call order 500n. So this would take 500 operations, this would take 1,000, this would take 1,500, and this would take 5,000. And so these times are, much worse than this n squared set of times. But if we look at the growth rate, we doubled the amount of data, we doubled the amount of time. We triple the amount of data, we triple the amount of time. 10 times as much data, 10 times as much time. Even though these numbers look larger, the growth rate is still linear. So order 500n is the same thing as order n. So I've got a little squiggle there. It says that, effectively it's the same thing. And, if this is the number of seconds it takes, yeah, 5,000 seconds is much worse than 100 seconds, right? But eventually, if I look at a big enough n, this is going to end up being better than that, right? Once n is bigger than 500, 500n is going to be smaller than n squared. So constants don't matter. All right, the second observation is lower order terms don't matter. So let's just look at our quadratic algorithm. And let's compare it to an algorithm which is order n squared plus n. So if n is 1, this is going to take 1, this is going to take 2. If n is 10, this will take 100, this will take 110. Hey, this doesn't look quadratic, right? I increased my amount of data by 10, and the complexity increased by 55, not by 100. So it looks like this is somehow not doing the same thing that that n squared would be doing. But let's go out to a larger value. Let's go out to n of 1,000. So order n squared is 1,000,000. Order n squared plus n is this number. And let's go out to n equals 1,000,000. So order n squared is 1,000,000,000,000. And order n squared plus n is going to look like this. Sorry, this needs extra zeros. It's going to look like this. All right, well, let's do some calculations and see what this growth rate actually is. So we know what this one is, right? Let me do that again. So there's 1,000,000,000,000, there's 1,000,000, and so this is a good 1,000,000x, right? So we increased n by 1,000. This increases by 1,000,000. But let's take a look at this case where we had order n squared plus n. And see what the growth rate is there. And it's 999,001. Very close to 1,000,000. So this is 1,000x. This increase was 1,000,000x. This increase was 999,000x. The larger n gets, the closer this is going to get to 1,000,000x. And so asymptotically, in the limit as n approaches infinity, the complexity of this is going to be the same as the complexity of that. So usually we can ignore these lower order order terms, we can say something like order of n squared plus n is similar to order n squared, asymptotically the same, meaning when you go out towards infinity, the difference between this and this becomes negligible. It gets smaller and smaller as n gets larger. So those are some thumbnail ideas about order of complexity. So in the problem set today, you're going to start with a simple single loop, do some time testing on it using the time command, and then you're going to add an inner loop and see how that works. And you're going to plot your data as you do this and get an idea what these graphs look like. And then ultimately you're going to add a third loop to the inside. And a third loop, 3 nested loops, might be something that happens like when we're doing matrix multiplication or some kind of matrix manipulation or working with higher dimensional arrays. And so we're just trying to get an idea for this order of complexity. And we're going to use this down the road when we start talking about different ways of storing and processing data. In particular, when we start comparing processing data in an array versus something that we call a linked list. And then when we go on to talking about binary trees, we'll see how to improve on this order of complexity. So this will be a tool that we're using, and today we're just trying to get some exposure to the basic idea, get some practice with the concepts. All right, see you next time.